Hello everyone, this is Sean Yu, your 5111TA, and today we'll be talking about transition metals in preparation for your final
today we'll be
exam.
discussing oxidation and reduction in preparation for your midterm treatment.
So here are the list of things that you need to know about
here are the
transition
things that
metals.
you need to know.
We'll be talking about these in detail. So first of all,
determining the
you need to know
oxidation
how to
state.
calculate the D electrons.
Second, balancing the reduction
So the number
equation.
of D electrons can
Third,
easily be
using
calculated
Faraday's law
by
to
subtracting
calculate the
oxidation
total
state
amount of charge
from the group
passed
number
in
of the
time.
transition level.
Fourth, determining the self.
So I listed some examples
using the
of
relationship
calculating D
delta G
electrons.
is equal to minus
So let's just
10
go
delta
over
G.
calculating D electrons
from
of
that,
iron 2+.
predicting whether a reaction is
So
homogeneous
iron 2+
or
have
homogeneous.
oxidation state of
Finally,
2
using their
and is
equation.
in group 8.
E.
So the D electron count should
So,
be 8
let's begin
minus 2.
by discussing
So
how you
60
determine the
electrons.
oxidation state. So when you determine the
Now,
oxidation state,
You also
follow
need to
these
know the
steps.
shape of the D orbitals
First,
for the transition
three
metals.
elements have oxidation number of 0.
So notice
Second,
that for
alkali
DYZ,
metals have
DXY,
oxidation
and
number of
DXZ,
1,
you have
while
lobes
alkali
lying
earth-like
in
metals
between the
have
axes.
oxidation number
While you for
Aluminum
for DZ
usually
squared
has
and DX squared minus Y squared, you have lobes lying along the
and
axis.
oxygen has oxidation number of -2,
Now,
except for peroxide.
let's talk about
where
crystal
oxygen
field
has
splitting
oxidation
diagram. A key concept in crystal field splitting
Hydrogen
diagram is
also
that you
usually
have
has
repulsion between the D
One,
electrons
except
and the
for
ligand.
metal hydrides where it has
So the D orbitals that have the least repulsion
Halogens
with the ligand
usually have
has the most stable energy.
And when you determine the oxidation number,
Okay,
you can
so
double check if it's correct
now you
by
have crystal
checking whether
field
the sum
diagram
of the
for
oxidation
octahedral, tetrahedral,
equal the net charge
and the square
of ion.
planar system. Notice
Now,
that for
let's
octahedral,
talk about
you
balancing
have
the
DZ squared and the
When
X
you
squared
balance the
minus
reduction
Y squared
equation,
at a
you
higher
first
energy
assign the
level than
oxidation.
the 3D
When you
orbitals
assign the
lying
oxidation numbers,
in between
you
axes,
can determine which
and the
species
pattern is
is
flipped for the
oxidized,
tetrahedral system.
which species is
And you have a little bit of complication in the square
and
planar
you
system.
write down the corresponding
Now, how do you
reduction
understand the complexity that arises in the square planar field?
and you
Well, an
balance
easy way
each
to think
path
about it
reaction
is,
using the
so for
acidic
square planar field, imagine you're
you
starting
use
with
water
an
to balance
octahedral field.
oxygen,
And
whereas you
imagine
use
that you are slowly
proton to
increasing the
balance
distance of the ligands
you multiply
lying
half
along the
reactions such that
z-axis.
the number of electrons
As a result of increasing the
oxidation
distance,
half
you
reaction
have the stabilization of the dz squared orbital, because
Finally, you
those
sum the
dz
half
squared
reactions.
have load lying along the z-axis. So you have dz squared
Now let's move on to discuss
lower in
how you
energy
determine the self.
compared to the x squared minus y
When
squared.
you determine the self,
The same
you
trend
use
goes
the
for
delta
dyz
E
and
of
dxz.
self is
Since
equal to
these two orbitals have
E
some component of
reduction
their
half
orbital
reaction minus
lying
the E
toward the
of oxidation.
z-axis, you have the stabilization.
And it is
compared to
very
the x
important
orbital.
that you don't multiply coefficients when you calculate the
Now,
self.
you also
This
need
is
to know
because
how to
E
calculate
is-
the crystal field stabilization energy.
And from the
So
relationship
as an
delta
illustration,
G
let's
is
talk
equal
about
to
manganese
E.
CO6.
We know that the reaction
So
is
you know that
homogeneous
manganese is 3+, so you have 4D electrons, and you know
and
that
as a note,
CO is a
galvanic
strong
cells
field
are
ligand.
the cell
So you
corresponding
place the 4
reaction
electrons
used to
on
drive
the lowest energy orbital, which is the
whereas
P2G set
electrolytic
here.
cells
And
are
for
the cells
each
where
electron placed
energy
on P2G set, you have a net stabilization of 2/5 of delta 0. So the
Now,
crystal field
let's talk about energy.
stabilization energy should be
In
4
Nernst
times
equation
negative 2/5
of
delta
delta
0
E of cell
plus
is equal
you
to
get
delta E
minus 8/5.
not
delta
of the
0.
cell minus RT over NN.
Now, how do you know a ligand
This
is
is
a
further
strong field
simplified to
or
delta
a
E
weak field?
delta E
Well, that's why we have the spectrochemical
Like-
series listed below.
log.
So
Of course, this
all you have to memorize is basically the fact that CO
and
and
if the
CO
reaction
minus
is in
is a strong
equilibrium,
field ligand,
Q is equal to Q.
and
And
water
you
and
have
ammonia is a medium strength
expression.
ligand, and halogens are weak field ligand. So
Now,
you will
let's
learn
talk about the
these trends
actual
in detail
question.
in more advanced chemistry classes, but for now just memorize a few examples of strong field and weak
So to
field.
solve this question, you use the mathematical cathode.
Now let's move on to our main business. So here are the questions from the actual final exam in the past.
As discussed
So first,
earlier, delta E
calculate the
cell
d electron count for iron 2.
cathode
We just discussed that iron 2
thus
has 60 electrons.
calculate the delta E of cell.
Now, draw the octahedral crystal field splitting diagram for
Write down
iron
the
2
oxygen.
for weak
So
and
we know
strong
that oxygen
octahedral
has
field.
an oxidation number of -2, and
Well,
we
for
denote the
weak
oxygen
field, you
X
should maximize the
instead of
number of
simply
parallel spins.
and
So you place the electrons on the EG set, and for strong field,
now
you try to
we have to
put
balance
as many
equation.
electrons on the
overall
lowest
reaction
energy
method.
orbital, which is the T2G cell.
So zinc oxidizes.
How do you calculate CFSE for high-spin iron 2?
and,
Well, you go back to the
oxidation
diagram,
reaction, and manganate is being
and for each electron placed on the
And we
T2G
balance
set, you have negative 2/5 of delta
oxygen
0, and for
water,
each electron in the EG set, you have 3/5 delta
be
0
multiplied
destabilization. So you sum it up and
necessary
get
conditions to
crystal field stabilizing energy
And
of
we
negative 2/5 delta.
and
How do you calculate
now,
CFSE?
which
for low
species is
spin?
a better
In
oxidizing?
that case, you place all your
So
electrons
an
in
oxidizing
the T2G set.
agent is a
Thus,
species
you
that
have CFSE
itself is
of
reduced
4/5.
while it oxidizes other species. So to
Now,
determine
with iron hexacyanide,
if a species is a
high-spin
better
or low
oxidizing agent,
I just
you have to
discussed that
compare
cyanide is a
the-
strong field
so
ligand.
a species that
thus you
has
have
a
low
higher
spin system
reduction
for iron
will
hexacyanide.
be a better oxidant.
Now calculate the
So,
octahedral
and since
crystal field splitting.
permanganate has a higher
Well,
reduction,
we know that delta E is
Plus,
always
you know
equal
that
to
permanganate
Hc over lambda.
better.
So you plug in all the numbers and convert it into kilojoule
Now,
per mole,
calculate the
and
current
you get 392
generated
kilojoule
by
of crystal field splitting
70.
energy. So this is the energy difference between EG and
So,
T2G.
Since 1 mole of electron contains 96.85
Now drawing the orbitals, that should be easy.
0.037
So for a molecule that
Coulomb.
have
So you
ligands
divide
placed along the
that
z-axis,
by time,
you can predict,
3600
according to the crystal field theory,
to get
that the orbitals line along or toward the z-axis
That
will
was
have
done.
net destabilization.
everyone's
So
good
you'll
luck.
have dz squared higher in energy compared to dyz. Now the final question. You're asked to draw a crystal field splitting diagram for octahedral crystal field and tetrahedral crystal field. So the net d electron count is 8, and for octahedral system you have 6 electrons in T2G set and 2 electrons on the EG set. So this is the same regardless of whether the ligand is strong field or weak field. And for tetrahedral diagram, you know that EG level is lower in energy, so you have a crystal field splitting diagram as shown here. And for both cases, you can explain the presence of paramagnetic species. So as a side note, when you draw a tetrahedral diagram, notice that you always have a high spin system, regardless of the ligand. So when you have a tetrahedral ligand field, you don't worry whether a ligand is high spin or low spin ligand. You always have a high spin system. Okay, that was the end of the review session, and everyone good luck with the final exam. This was Sean Yu.